Hi everyone, my name's Abraham Gonzalez. This is Jerry. We are both graduate students at UC Berkeley, and we're here to talk about the Berkeley Out-of-Order Machine, otherwise known as BOOM. So a little bit of an outline of what we're going to talk about today. First, we're going to give you an introduction. What is this BOOM that we're talking about? We're going to talk about the microarchitecture because it's a core, give some comparisons to other cores that are out there, give some performance metrics, some features that the core has, why you might want to use it, and then how it's nice for research. So a little bit of an overview. So as I mentioned earlier, we are graduate students at Berkeley, so this is a Berkeley architecture research project. It was initially started by Chris Celio, but he has now graduated and he's working at a company called Esperanto. So it has been taken up by 3 other graduate students. So Jerry, I, and another graduate student called Ben. It is an out-of-order superscalar RISC-V core. So different than Rocket. Rocket's an in-order core. We're an out-of-order core. And the nice thing is that we run RV64GC and some parts of RV32. This has been taped out already, so it is silicon proven and it has been synthesized, or it is synthesizable, excuse me. Finally, as Jack mentioned earlier, this is written using their language, Chisel 3 source code, so it's 18K lines of code. So if you're interested in touching and using Chisel, this is a great opportunity to use that. Finally, and we want to emphasize this does boot Linux and Fedora, and so it does run real workloads. The picture that's up there shows it running RV Linux and sending out a tweet. And then, of course, as a Berkeley project, it is BSD licensed. So since this is part of the Berkeley research ecosystem, it involves a lot of the different projects that have come out of Berkeley. One of them is Chisel, which we already talked about a little bit earlier in the day, but it also uses Fertile, and then you can also hook it into things like Hammer and FireSim. FireSim is the talk afterwards, so I'll let them explain a little bit more about what it does. But you can essentially pass this through both ASIC flows and through FPGA flows. So if you want to do any sort of simulation in the cloud on the FPGA, you can do it through that resource. Or if you want to try to tape out a chip, you can run it through Hammer. So it hooks into both of those fairly well. Finally, it has been used in many places. So it's been used a lot of places in academia. I believe Jose just mentioned it earlier in the previous talk. And then it also has been used for a lot of Berkeley projects inside. We like to use this because it is a good representation of an out-of-order core, and it gives us introspection on a beefy core. And as I mentioned earlier, it has been taped out. So Broom was the tape out that Chris did right before he graduated. And there's other tape outs that are in the works. So if you're still interested in the project, you can hear about it a little bit sooner since these aren't out yet. So to give a little bit of a reference of what our core looks like in comparison to others. So these are a couple of cores coming out of ARM. So these are the Cortex family of processors, starting from the A9 all the way to the 73. So I believe the A9 was done in 2006, but as you can see, for an out-of-order core, it's fairly standard. You have your fetch, your different stages of decode and rename into your issue queues, and then you actually send it out into the execution units. There's variation between having a unified issue queue versus having them separated out between all the execution units. But basically variations on this where you either split up the issue queues, change the amount of pipeline stages, things of this sort. So similar to these cores, BOOM looks like this. So at the upper part of the picture, you see all the different stages that we have, and then you have in the front end, you have things like a BTB and a RAS, a return address stack. You have the backing predictor, which is your more complicated predictor like Tage, Gshare, et cetera, and then you have the decoupling from the fetch buffer from the front end, and then you go into your decode rename into your issue queues, so you can actually have unified and separated ones, and then you go into your unified physical register file, and then into all of your execution units in the back end. So a fairly standard modern out-of-order core, I would say. So looking at performance, so we're comparing ourselves mainly to like the A15 and A9. So we normally we're normally in between kind of the two in terms of performance. So we're in the red, and the A15 and A9 are the blue and the green. I don't know if it's flickering on your end, but hopefully not. But Yeah, so we're normally in between the two in terms of performance. These numbers are gotten during the Broom tape out, so performance has changed a little bit, but we're making some changes to the core, so we don't want to get a performance snapshot just yet. So what are the features? It's a core, that's great. What are some of the cool things that I want to point out? So Chisel allows you to write a lot of parameterized generators. Similar to Rocket, you're able to basically change everything about the core. So whether you want to change the size of your issue queues, you want to change the amount of execution units, you have a lot of leeway into changing all those knobs. Additionally, since it is integrated in the Rocket chip ecosystem, it is essentially a drop-in replacement for the Rocket core. So you can attach it to a bunch of different peripherals, rock accelerators, things of that sort. If you're doing research or you're trying to figure out what's happening inside of the core, you have things like hardware performance counters. So you can see the amount of mispredicts that it has, or if you implemented something in the core, you can see, is it actually working or not? You can mess around with the issue queues similar to how ARM has like a unified issue queue or separated ones for different execution units. So you can kind of play around with that. It's really easy to change up the amount of functional units that you have. So for example, in the picture, you have 3 functional units that have different things inside of them, and then depending on the configuration, you can change it around and have more or less. And we also have like this framework, so you can actually change up your functional units fairly easily. So if you want to write your own, you can go ahead and do that, and it's not too much effort. And a lot of the extra logic around bypassing, speculation is kind of automatically done for you. So all you have to do is write the main crux of that functional unit. What is it doing? So another feature that we want to point out here is branch prediction. So as I mentioned before, we have a single cycle branch predictor for simple loops such as the BTB, and it has a bimodal table and a return address stack. But you also have a more complicated branch predictor. And the nice thing about these is that with these branch predictors, you can actually kind of swap in and out whichever branch predictor that you want. So if you want to run Tage, you can kind of run that in a configuration. If you want to run it with gshare, you can kind of swap it in, swap it out. So you have the leeway to change up your more complicated predictor. And the other thing is that we create this interface. Since this is what we call the abstract predictor, we create this interface so you can implement your own branch predictor. So if you're a researcher, you're just someone who wants to mess around with looking at an out-of-order core and how to do branch prediction, you can essentially cut out this section, replace your own branch predictor, and then go from there and debug it and see how it works in the actual core. Similarly, if you're on the accelerator side and you're really excited about the landscape of accelerators, you can work with the ROC interface. So similar to Rocket, we have a subset of the ROC interface, so you can add your own accelerator. So for example, if you want to work with a vector accelerator, you can snap in Latch-Up, which is a Berkeley vector accelerator. Or if you want to be the next Google Edge TPU or some TPU-like core, you can create your own systolic array accelerator and kind of attach it in. So there's a lot of leeway. You can create your own accelerator and just snap it in and see how it works. Next up is Jerry, who's going to talk about some of the research avenues that you can do with the core.
Right, so I'm Jerry. I'm going to talk about some of the applications of Boom for academic computer architecture research. So starting off, let's ask the question, why did Chris Salio spend many years of his PhD doing this engineering, and why is there currently a new generation of graduate students who are going to continue maintaining and working on this engineering project? And it all boils down to really the end of Moore's law. Since we cannot rely on steady improvements in processor technology to drive improvements in processor performance, we have to take a look back at the design fundamentals behind how modern high-performance cores are built and rethink them. So in a world without an open source, out-of-order high-performance core, you sort of had to fall back on software simulation to do this research. So with software simulators, you naturally inherit many of the disadvantages of these simulators. They don't provide the real RTL, so you can't accurately model power and area. You can't actually tape anything out because, again, it's just software simulation. And furthermore, these simulators are rather slow. They run on the order of kilohertz. So you really can't run your real live trillion cycle workloads without waiting for weeks for these simulations to finish. So in contrast to that, Boom is a first-class member of the Berkeley Architecture Research Infrastructure. So we provide an open source RTL of a real silicon-proven core in an ecosystem where we provide a lot of agile, highly productive tools for doing research. So we can do agile tape outs for power and area validation. We're integrated into a lot of simulation frameworks and physical synthesis frameworks like Hammer and FireSim, as Abe mentioned. And what this essentially lets us do is get results back from our research really quickly. We can very quickly build an FPGA image of Boom and run it in the cloud, running simulations out on the order of hundreds of megahertz, so we can run real data center workloads and evaluate Boom. So in summary, we have this really great infrastructure for computer architecture research. And what are the kinds of problems which we can explore using this infrastructure? Well, one area is fundamentally microarchitecture. So this is sort of alluding back to the end of Moore's law. We can't really rely on manufacturing improvements to drive performance, so we have to look back at the design fundamentals of microarchitectures. So in general, the hardware costs of a very wide out-of-order machine come from two components. There's a multi-ported register file and the scheduling logic, which wakes up operands, wakes up instructions in the issue queues and sends them to the execution units. So this is based on some work that was sort of proven in simulation about 15 years ago, but only now do we have the infrastructure available to actually implement something like this physically. So the idea is ring scalar, and what it's essentially saying is by reorganizing some of these structures, splitting up and reorganizing some of these structures, the register files and the issue queues, we can drastically reduce the cost, the complexity, and the area costs of building an out-of-order machine without sacrificing too much in terms of performance. So this lets us more quickly build smaller, efficient, high-performance processors. So Boom here serves as a baseline implementation as a point of comparison. And because it's implemented in Chisel, which is highly productive and very flexible for us, we can really quickly do design space exploration across various design points and explore microarchitecture here. So the next research area which we've been looking into and which has been especially important in the past year is security. So early last year in January, the revelation of the Spectre attacks essentially revealed that there were fundamental issues with many of the design techniques behind modern high-performance cores. So in essence, many of these techniques, these fundamental techniques like branch prediction, speculation, caching even, they left behind practically exploitable vulnerabilities in these cores. And at the same time, as I'm sure you're all aware, this trend towards open source hardware means that more and more open source chips are entering the world and can potentially get used in a security-aware application. And this will give attackers the unprecedented opportunity to reason about the behaviors of these cores at a very fine-grained level and produce very precise timing attacks on these cores. So we'd like to believe that the open source hardware community can sort of follow in the footsteps of the open source software community in responding to this and sort of come to a world where we rely on security through openness and design rather than security through obscurity. So with an open source core that is vulnerable to these speculative execution attacks, in this case Boom, we can try to provide an open research platform for evaluating various security defenses and mitigations and sort of create a community of people who can sort of come together and validate how effective are these mitigations and make sure that they're doing what we really say they are. And also because we're integrated in this high productive research environment, it makes it really easy for us to do design space exploration over the space of possible mitigations and defenses. So at Berkeley last year, we started some preliminary work going down this avenue. So step one for this was we take a look at all the literature on demonstrated attacks on commercial x86 ARM cores and show that they are replicable on our Boom out-of-order academic core. Step two is we build some simple preliminary mitigations as part of Boom. Step three, we run this through all our tooling, our infrastructure, and get quick results back showing what is the impact of these mitigations on performance, area, and implementation. So starting with step one, we replicated the simplest variant of Spectre on Boom. So what's going on here is we're launching a FireSim accelerated FPGA simulation of Boom. So this is a cycle-accurate simulation of a Boom core. And on the left, the attack code is going to run. It's going to start to just print out the binary of the victim function. So you can see, I think on the left is what it's predicting, and on the right is what it's actually supposed to be. Skip ahead a little bit. So now it's printing the victim function code. And now we get to the part where it starts printing out the secret array in the victim. So it does look like this is just printing out lines of code, but behind the scenes, this is a replicated Spectre v1 attack running on Boom, running at about 100 megahertz on FireSim. So this is pretty cool for us because it showed that we can replicate and simulate these attacks pretty quickly on our infrastructure. Right. So now that we know these attacks work, we wanted to think, what is the simplest mitigation we could think of to stop these attacks? So without going into too much detail over how this attack works, essentially it's leveraging speculation and the results of speculation in the L1 data cache to give the attacker a side channel from which it can extract information from the victim code. So a simple mitigation would be to prevent speculated instructions from affecting the L1 data cache state. And on the right, we sort of have a block diagram for the L1 decache. So we implemented this speculation buffer, which holds uncommitted refill data coming out from L2 and prevents it from writing into the tags and data arrays until we are sure that they have been committed. So on a mispredict, the buffers would be cleared and the results of speculation would not be seen by the rest of the core. So we evaluated this again in our FireSim infrastructure and basically showed that after implementing this mitigation, the L1 side channel could not really be exploited easily by speculation. Because we were pretty clever with how we implemented this, so we didn't turn off speculation completely, so there was a minimal impact on performance on a workload. And we were also clever to implement our speculation buffer as single-ported memories, so there wasn't a significant area overhead for this buffer. So this work was pretty preliminary, but it is pretty promising because it shows that we can perform this line of research in the future and look at more interesting mitigations and defenses. So, there's a lot of other side channels in the core, TLBs, branch predictions, L2s. Can we apply similar strategies or different strategies to protect those side channels? And also, if we can't solve the speculation issue completely, maybe we can just solve the security issue for a small component. So there's been discussion over having secure enclaves, which are smaller, more secure segments of programs. Can we hide the execution behavior of the secure enclave from an attacker code? So this is all really interesting research, which we hope to be doing more of in the future, leveraging Boom. So in conclusion, the Berkeley Out-of-Order Machine is a synthesizable RV64GC out-of-order core. It's open source, expressed in Chisel 3, so a high productive language. It boots Linux and Fedora, runs on FireSim, runs on FPGAs, and it runs real workloads. And it's been integrated in our research ecosystem, so we can do high productive research using Boom. And outside of Berkeley, we've also seen some interest from commercial companies as well. So Chris Celio, after taking Boom to Esperanto, that work sort of evolved eventually into their own commercial core, which is partially derived from Boom in some way. And on the online community side, we've recently put up a lot of documentation, website, and we're getting a lot of traffic to our GitHub and websites. So with that, I think we should turn it over to some questions. Thanks.
Okay, so you showed using the buffering L1 catch, then only clearing it whenever the instructions in it were declared non-speculative. Yeah. What other techniques did you consider for preventing attacks?
So this one, we sort of chose this technique initially for the class because this was part of a class project. We chose this technique because it was the easiest to implement. There are other techniques out there that that weren't reasonable for us to implement quickly, such as you can sort of randomize where things go in the cache so that it's difficult for an attacker to observe. But given our time constraints, we want to do the fastest, simplest mitigation possible, which is why we chose this buffering approach.
Okay. And it was easy to do in Boom.
So.
I have kind of a broad question that may not have a good answer, but one of your diagrams or slides showed that the was Intel Ivy Bridge had about 2 instructions per cycle, and everything else was lower than that. Do you have like a summary of why that is? What are they doing that's making that so much better than all the other examples?
Well, if we knew, then.
Okay. Okay.
But I think, so some of the areas which we are aware where Boom is a little deficient compared to modern out-of-order cores is there's like the branch prediction and the data cache. So in branch prediction, it's really because we have a fairly complex branch predictor that is prone to bugs. And Abe's been working pretty hard on resolving many of those issues. And so once that's fixed, we expect our performance to jump up a little bit. So also these numbers are from Boom v2. So this was a Boom version that was designed to be for physical implementation. So Chris did a lot of things that ended up hurting branch prediction for this version, but in the name of for the sake of getting a tape out, it was necessary. And the other component of Boom, which is hurting its performance, is our data cache is single ported, so we can do 1 8-byte read or write per cycle. A lot of the other modern out-of-order cores are dual ported, and they can read out 32 bytes per cycle at most sometimes.
Okay, another question, what other bottlenecks do you have in it?
Oh, man. That we're aware of.
At least it's not the x86.
Yeah, well, okay, so atomics are kind of slow right now. So another issue is when the RISC-V memory consistency model was ratified, we had to sort of hack the way our load store unit worked. So we do follow the memory consistency model, but we are perhaps over-aggressive in doing so. So we often say we have a memory ordering failure when in reality none has occurred. So that's something that will get fixed eventually. I would say the biggest bottleneck is probably data cache and branch prediction by far. Yeah.
So one of the problem of Rocket Core was when you modify the code, if you do JIT, some modifications of a code, and then you try to execute that code, you have to flash cache, like instruction cache to reload that. Do you have any plans to evaluate JIT performance on Boom?
No, we have not thought that far yet, no. But I know there is people at RISC-V working on improving JIT support in the ISA, but that is still some time away, I think.
One quick question. In one of the slides, you showed Tage on the branch predictor, but I don't think it's pushed upstream. Is it there?
It is, yes.
Is it?
Yes.
Okay.
So there is. Sorry, I should probably move closer to the mic. So right now, there's actually a 5th branch predictor implementation, which is using the bimodal table too. But all of these are upstream, and so you can actually see these in our repo right now. Like I said, there is BPU bugs currently. They're getting fixed along the way. So sooner rather than later, I hope to have pretty good performance, at least on G-Share, and then Tage is a little bit more of a longer-term issue, but hopefully by the end of the summer, we'll see. Branch predictors are notorious for bugs, so we'll see.
Anything else? Let's thank our speakers again.